So our next talk is by Craig Neal, who will be telling us about regolith materials for ISRU in vacuum conditions, effects of phase evolution, character, and composition of X-ray photoelectron spectroscopy, and in situ calorimetry.
Hello, everyone. Can you hear me okay?
Yes, we can't see you though. If you feel like you want to share your video, you can.
So today I'd like to share some research that we're doing at the University of Central Florida in collaboration between Dr. Neal in the Material Science and Engineering Department and Dr. Britt in the Physics Department, all under the Center for Lunar and Asteroid Surface Science. So in particular, in this study, we're looking at a unique asteroid.
Craig, sorry to interrupt. Your sound is cutting in and out a little bit.
Okay. I'll see about changing headphones here. Okay, if you could let me know if this is any better. So we're looking at a little bit better. So we're looking at an asteroid regolith material, and in particular, we want to look at this material to focus on some of the engineering consequences of using this regolith material for ISRU. So, in keeping with that, we want to use a material that has a crystal structure and a composition that is relevant to the asteroid regolith. And we want to explore properties that are important for engineering applications. So in this case, we'll be looking at Antigorite, which is a serpentine structured material that's highly porous and has a low density. So this readily lends itself as a functional material because it can allow for catalysis with its open structure. It has a lot of surface sites that can react with certain materials. It can also take chemicals out of the environment in the same manner, and can also be used as an energy material because of the porous structure, allowing for charge transfer and sequestration of charged ions. So Antigorite is a silicate, and a hydrated silicate that also contains magnesium and iron. So we want to take this material and we want to look at its temperature sensitivity. And in keeping with describing the material in outer space relevant conditions, we are going to test the material in an inert atmosphere, in air, and then under vacuum. So the first thing we did was look at the materials, or the influence of particle size. So in doing this, we took an unsieved fraction of Antigorite and compared it against sieved fractions of greater than 212 microns and less than 53. And in doing BET surface area measurements, we found there was a weak correlation between the particle size being the small fraction or the larger fraction, and attribute this to the high porosity of the material. So the porosity dominates the surface area rather than the actual nominal surface area. So we chose to use the smaller fraction because a lot of the applications in using this as a functional material relate to surface reactions. So we want to increase the amount of surface area, nominal surface area if we can. So in doing so, all our subsequent experiments involve grains with less than 53 micron. So here I have thermogravimetric analysis and differential scanning calorimetry up to 1,000 degrees in an inert atmosphere under nitrogen flow at 1 atmosphere versus under vacuum conditions. So there's 5 peaks labeled here, and this is all for Antigorite. Peak 1 is the loss of weakly absorbed water species. 2 is related to pore reconstruction. 3 is the beginning of a dehydration process, which will be most important for the endpoint material. and use of the material in application. So that one at peak 3, we actually have formation of a hydrated phyllosilicate and then a fraction of olivine. And then at peak 4, we have complete dehydration, and 5 is conversion completely to olivine materials. So you can see in the vacuum environment relative to the inert atmosphere, peak 3 is more comparable to peak 5 in the vacuum environment relative to inert. In the inert environment, peak 5 is very much higher. So we would say that under vacuum conditions, we have more use of that hydrated material or more evolution of these phases, and it's not available for transformation in peak 5. So this is important for temperature processing of the material, and also further suggests this the necessity of the space-similar environments. Okay, so in doing X-ray diffraction studies on the materials in each of these environments up at different temperatures, we can look at the actual phase composition as it changes temperature. And so a lot of these, it supports the description of above 600 degrees. We have loss of Antigorite and formation of forsterite and enstatite. And so that's represented here, but also in the red highlighted region, we have an increased peak under vacuum relative to the inert environment. This is really the most significant change that we can see from the XRD study, and suggests either that it's an iron-rich phaolite phase, or it could also be a greater production of forsterite over enstatite, which is reasonable considering in the DSC environment, we saw a large peak 3, where we have that initial formation of a hydrous material and decomposition of Antigorite. So we would say that the enstatite, which has greater oxygen content, would be less favorable to be formed in this vacuum environment because it's consumed earlier in the reaction. Okay. So now that we have these impressions of what's going on physically and what phases are formed, we want to look at the chemical composition to really describe what's happening at each of these points in processing material. So in doing so, we did X-ray photoelectron spectroscopy, and we looked at specifically spectra for magnesium, iron, silicon, and oxygen, and looked at the relative amounts of each of these, as well as probing the chemical states for certain material, certain of the elements. So first here, this is a survey scan that just shows the entire range, the inclusion of all of the elements. And in comparing the stoichiometry of our material versus an idealized material, we see it's comparable stoichiometry. So any changes that we find experimentally, we can relate to the process. So here we have a direct comparison among a control unheated material heated to 1,000 degrees in air, nitrogen, or vacuum, and we see the stoichiometric implications of each of these. And so the real takeaway, with heating, there's greater oxygenation in air, nitrogen, or vacuum, although we see for the vacuum material a decrease in oxygen and of the metals composing the material. So something to consider here is that X-ray photoelectron spectroscopy is a surface characterization method. So in looking at that, we know from the DSC and thermogravimetric analysis measurements, the overall weight loss that happens with heating to 1,000 degrees is the same, independent of the heating environment. So we know that the components are not being lost, they're reassembling for the most part, or are lost in the same proportions. So when we have this change in stoichiometry, it suggests that it's formation of new phases of unique character. So now we've broken down each element and taken a spectrum from each of these. In considering the oxygen, there are several peaks attributed to it, and it's specific to the bonding chemical environment surrounding the material. And we see that they're fairly comparable for but in the vacuum, we see a clear distinction where there's a greater or a more comparable amount of the hydrated species and magnesium oxide phase. But so we look into the magnesium spectrum, iron later on. So here, the graphs show comparable distribution of magnesium oxide and of metallic magnesium. So we think, based on the previous measurements, that there's not much of a change in the oxidation of magnesium relative to the other components. So moving to iron now, we look at, has a more complicated spectra because of its increased number of redox states available to it. And if you look at the highlighted peaks here, related to 2+ and 3+ redox state iron, you can see that under vacuum condition, the 3+ state is much more highly favored compared to the 2+. So it's more oxidized, more oxygen directly interfacing with the iron. And based on the stoichiometry that we saw in from the survey spectra, we would think that iron is directly interacting with oxygen, perhaps at a subsurface location. So the surface is silicon rich when it's been heated, although the oxygen that was in the material and distributed is now more coordinated with iron and moved below the surface.
It's been 10 minutes.
In conclusion, and for the future, this study shows the value in measuring or evaluating materials in environments that are more reflective of how they would be in our space, and especially in considering how the materials change as functional, so how their surface changes even if the phase composition is similar in related materials. We also saw that there were specifically changes in the distribution of instantite or forsterite, and then also the oxidation states of iron. So in continuing this research, we want to look at stronger vacuum environments and see if there's a trend in this phenomenon with increasing vacuum, just where the processes end up on a phase diagram. And also the kinetic considerations of the thermal treatment, how if the distribution of phases will change with increased time at each temperature, and then also the functional implications of the oxygen loss at the surface. So if we wanted to form our own phase, we could, of a relevant material, maybe for catalysis, we're thinking to do maybe a metal oxide nanoparticle synthesis on this Antigorite substrate. And that could be accomplished by the dehydration of the surface and the oxidation of the metal salts to produce nanophases and a functional material. Okay.
All right, thank you for an excellent talk. In the interest of time, we are going to move directly to our next talk. So if you have any questions for Craig, you can ask them in the discussion section later.